Morning, everyone. We're going to give everybody about another 30 seconds or so to enter the room before we officially start today's webinar. Hello, and welcome to today's APT webinar, Rapid Room Temperature Desensitization of Stainless Steels, Atomic Scale Insights by Correlative Atom Probe Tomography and Electron Microscopy. Today's webinar features work from Kamika's newest team member, Senior Applications Engineer Kasturi Sazrahar, and University of Wisconsin Professor Kumar Sidrahara. Kamika's own Dr. Catherine Rice will also join our Q&A session. As always, please use the Q&A widget to submit questions. This webinar is being recorded and will be available with all of our previous webinars on our Thinkific platform. And with that, we can begin today's webinar.
Okay, thank you, Steve. Hello, everyone. It's my great pleasure to have the opportunity to describe this work that we have done as part of an excellent collaboration between the University of Wisconsin and Kamika here in Madison. So as you can see, the topic is on rapid room temperature healing or desensitization of sensitized stainless steels and how atom probe tomography and correlative electron microscopy were so crucial in understanding this phenomena. So let's get started. To give you a brief introduction about the concept of sensitization to those who are not familiar, stainless steels undergo a phenomenon called sensitization. This is a very well-known age-old problem when they're subjected to heat treatment in temperature regimes of 450 to 600 degrees Celsius or sometimes 800 degrees Celsius for a particular amount of time. They undergo sensitization. This heat treatment can occur in a number of different practical situations during fabrication, manufacturing. Typically, welding is a very common example. The heat affected zone or the HIZ of fusion welds are typically sensitized. It's a major problem in a number of different industries, including nuclear, oil and gas, chemical processing, transportation, and so on. And traditionally, healing or remediating sensitized stainless steels require expensive long-term heat treatments because you need to reverse the phase transformations. And what exactly is this sensitization? Classical knowledge from a metallurgy textbook tells you that stainless steels have a small amount of carbon, typically 0.1% or lower, and when they're subjected to this heat treatment, they form chromium carbides, but the carbon content is not sufficient enough for a homogeneous precipitation of chromium carbides, so they only form along the grain boundaries like this. But then as a consequence of this carbide formation, there is a natural depletion of chromium in the vicinity of the carbides. So there's chromium that goes out of solid solution. So, and typically it goes below the critical amount of chromium that's needed for passivation. So for corrosion resistance, you need to form a passive oxide film, a very thin passive oxide film on stainless steel surfaces. And that stable passive film requires at least 12% of chromium to be in solid solution. And as a consequence of this carbide precipitation, this solid solution chromium content goes down below that threshold. And that gives rise to intergranular corrosion. And it's a problem in several applications. In our research work, we were investigating this in the context of the nuclear fuel storage cycle. So the bottom figure here shows a so-called dry cask storage canister, which is basically a very long sheet of stainless steel that's welded to form a cylinder. So a fusion weld goes here, and you have a sensitized stainless steel that's in the heat affected zone. So to give you a little bit of context, um, these canisters are used as interim storage sites for used nuclear fuel rods. So before the spent nuclear fission fuel goes into a permanent repository, because of logistical reasons, they have to be stored in these interim storage sites, and they may have to be stored for anywhere between the next 50 to 60 or even more years, depending on availability of permanent storage sites. So there is a problem of corrosion that can happen here when they're exposed for extended periods of time to, corrosive environments like marine environments and so on, which is very typical for these storage canisters. So the idea was we cannot afford to use heat treatments in this application where you have used nuclear fuel. So we were exploring rapid room temperature surface peening technologies for remediation. So I'll go into the details of the technology in just the coming slides, but to give you a preview into the effectiveness of these technologies, you can see the post-corrosion SEM images of a sensitized stainless steel and a surface peen stainless steel, surface peen sensitized. So the as sensitized stainless steel shows the classical intergranular corrosion behavior with very deep localized grain boundary attack to an extent that there is some amount of grain pull out that's taking place. So that's rapid corrosion. But if you look at the bottom right image of surface treated, sensitized stainless steel, the intergranular corrosion to a great extent has been eliminated. So, and the corrosion rate has gone down. So how exactly this takes place and what are the details? That's going to be the topic of the talk today. So we investigated a technology called ultrasonic nanocrystalline surface modification. In the literature, people call this with different names. But essentially what this process consists of is a mechanically loaded hard tip, typically a tungsten carbide tip, that's subjected to a static load, and then that is ultrasonically vibrated in the vertical direction, and the whole probe is rastered on the horizontal surface of the sample. So it goes by a rastering mechanism, and in the process of the ultrasonic vibrations, it introduces very high strain rate deformation, where the strain rates can go as high as 10 to the power 4 second inverse. So in different materials, this high strain rate deformation gives rise to several deformation mechanisms, which are mostly associated with mechanical hardening. So there is excessive grain refinement to the extent that you can have nanocrystalline materials forming in the near surface regions. And in the case of austenitic stainless steel, you will also have a deformation-induced martensitic transformation, as I'll show you in the coming slides. So that's the technology that we have utilized in this work. So these are the typical process parameters. There's a frequency of the ultrasonic vibration of the loaded tip. That's of the order of kilohertz. And then there's a feed rate and a step size and the load that you apply that you can all engineer for a given application. When we performed our study to investigate this technology, we varied the applied loads and for the purpose of the study, and we used high carbon stainless steel, and that was subjected to sensitization by heating it at 650 degrees Celsius for 48 hours. We used a relatively high carbon, basically to exacerbate the effect of sensitization. More carbon in the stainless steel limits, you can have more carbide and chrome dissolution along the chrome depletion along the grain boundaries. So that was the process, and the effect of the process. I want to give you an overview of the microstructural transformations before we go into the details of the characterization. So these are cross-sectional SEM images of the different UNSM, we call the process UNSM, treated samples. So we are looking at the microstructure as a function of depth from the treated surface in the cross-section. So first of all, you can see a lot of deformation-related features. You can see, to an extent, grain refinement. And in the deeper regions, you can see some kind of deformation bands. And the density of all these features increases if you increase the load. So what exactly these deformation bands are composed of, we'll come to in a moment. From a macroscopic perspective, the UNSM treatment gives rise to a surface hardening, a substantial amount. The surface hardness is almost increased by 2 to 3 times. And the depth of influence is also quite substantial. It can influence close to 600 to 800 microns of the material from the surface. And in terms of the phase constitution, so you can see here from the XRD patterns, the black diffractogram corresponds to the reference material, which shows an austenitic matrix with a small amount of martensite that remains. But if you look at the UNSM treated diffraction patterns, you can see that most of the austenite has transformed into martensite, particularly at the higher loads. So at least within the X-ray penetration depth, which is close to 10 to 20 microns, it's completely martensite in the material now. In addition, we also measured residual stresses in the material by X-ray diffraction methods. And you can see that there is a compressive residual stress denoted by the negative sign. And the compressive residual stress, the magnitude increases with increasing load. So all these microstructural features, basically grain refinement, the surface hardening, the phase transformation, compressive residual stress, all of them are contributing to a corrosion enhancement. So these are results from a potentiodynamic polarization test, the classical or most commonly used corrosion evaluation method conducted in synthetic seawater. So the black line again corresponds to the as sensitized material. And the other curves correspond to the UNSM treated material. And you can see that from multiple perspectives of electrochemical corrosion metrics, the corrosion performance has improved. You can see a higher pitting potential compared to the reference sensitized material. The corrosion currents are lower, and the open circuit potential is also nobler. So there is tremendous improvement in the corrosion resistance of the sensitized stainless steel when subjected to this surface cleaning technology. So the question is, it's great to see these results from an engineering point of view. It does tell you that the sensitization problem is being remediated to a great extent. But the question still remains, how do these processes, how does this surface deformation treatment interact with the microstructure to alleviate the intergranular corrosion? So none of these characterization techniques really answers that question as to how the chrome depletion in the grain boundary regions, which is known to be responsible for sensitization, how is that being eliminated? So that is a question that still needs to be answered. So our hypothesis from an intuitive metallurgical understanding is probably these carbides are getting disintegrated or to some extent dissolved as a consequence of this high strain rate, high strain deformation. So this was a hypothesis which we needed to investigate and for which we needed much higher resolution characterization. So that's where we're moving towards now. So we first started off with electron microscopy investigations. So here is a cross-sectional EBSD map. So again, we're looking at the cross-section of the material. So the red line indicates the surface that was subjected to this treatment, and then we're looking as a function of depth from the surface. So the top surface is extremely deformed and it's transformed into martensite, so it does not give sufficient signal to noise ratio in the Kikuchi pattern, so you cannot index that. And then you see deformed regions, and the extent of deformation goes down naturally as you go in depth with respect to the surface. So for our high resolution characterizations, we picked samples from multiple depths. But then for the purpose of today's talk, I wanted to focus on samples that we extracted from this depth, about 80 microns from the surface, because it presents a representation of multiple stages of deformation. So when in surface engineering technologies, when we look at cross sections of the material, we can probe different stages of the process induced transformations when we look at samples at different depths. So in this particular sample extracted from 80 microns below the surface, in the TEM, you can once again see these deformation bands. And what these deformation bands are composed of, when you look at the selected area electron diffraction pattern, you can see classical twinning. So you have the reciprocal lattice corresponding to the matrix and a twinned lattice. And in addition, we also see an alpha prime martensite, the reciprocal lattice shown by the red vector basis. So, so that means these deformation bands in this region are composed of deformation twins and alpha prime martensite. So, and if you look at the high resolution image, you can see the twins, and it's very interesting to see that the twin thickness is very small. The twin width is just about a couple of nanometers. So essentially, the important points here are deformation bands are composed of nanotwins and alpha prime martensite. And the literature also supports this idea that for these high strain rate deformation processes, the strain-induced martensite formation mechanism goes through deformation twinning. So you first form twins, and the sites of twin intersections are nucleation sites for the subsequent martensite transformation. But then again, all of this gives structural information. What we don't know is how these deformation mechanisms interact with the chemical composition distribution within the sample, which is what is most important for answering the questions that we had. So that's where the crucial insights from atom probe tomography come in. So we extracted samples from the same depth that I'm showing here below the surface, both from a reference sensitized material and from a UNSM treated material. These are atom probe reconstructions from the reference sensitized material. So these are two different perspective views of the same carbide. So this is the sensitization induced chromium carbide that has formed. And it has really formed on a grain boundary. The grain boundary can be seen from this ion density map shown here. So we are taking an ion density map along the surface indicated by this box. And that box clearly shows the ion density map shows a grain boundary trace here. So we have a carbide that has formed very close to the grain boundary. And this shows an overview of the elemental distributions, the important ones at least here. So what is important to be seen is the composition distribution between the carbide and the matrix. So if you look at the chromium profile, zoomed in here in this inset, in the austenitic matrix very close to the carbide, the chromium content goes below 10%. It's almost going to 7 to 8%. And that is classically expected from sensitization. That's what textbook knowledge tells us. And we see that very evidently here from the atom probe results. So that is nice, but the more important thing is how does this get transformed in the surface engineered material? So these are atom probe results from the UNSM treated sample. Um, so again, so the first thing we saw here, the carbides are very much intact. They have the chromium carbides have not gotten disintegrated or at least completely disintegrated or dissolved into the matrix. They're very well intact. Their size is rather comparable to the sensitized material. And if you look at the chromium content distribution, this is where you start to see very interesting things. So now here, the matrix, the lowest chromium content in the matrix is about 10%, and it's close to 11% or so. So that already tells us that, when the lowest chromium content is close to the chromium content required for passivity, that kind of explains us the, reason why intergranular corrosion is greatly reduced in this material. So there is some amount of chromium homogenization that's taking place. So now the question is the chromium coming from the carbide into the matrix? Like, is there some kind of dissolution of the carbide, or there is homogenization in the matrix? So answers to that question will come up now. So one thing that can be seen here is the interface width, or the transition from the matrix to the carbide is not very different for this sample and the previous sample, the sensitized as sensitized sample. So that does not tell us that the carbide is dissolving. So we looked at, and there is a theoretical basis also which kind of supports the idea that chromium carbides are relatively very stable. So in the literature, there have been different approaches using ab initio and Calfett-based thermodynamic calculations to see if a deformation-induced mechanisms can actually destabilize certain carbides. So it is possible to destabilize less stable carbides like iron carbide, cementite, by high strain rate deformation. So these are on the left side, you see destabilization energy contributions, which come up from deformation, and the green bars show the threshold destabilization energy, or the chemical stabilization energy of the carbide that needs to be overcome by deformation. So if the orange is greater than the green, basically the carbide can be destabilized. So for cementite, it's possible, but chromium carbide is extremely stable. The affinity between chromium and carbon is very high. So therefore, deformation cannot really destabilize the carbide. So the question comes, where is the chromium homogenization, happening? So if it's not coming from the carbide, then what is happening in the matrix? So then we started looking at the atom probe data in much more detail. And here I'm going to show the distribution of chromium content in 3 dimensions using the chromium isoconcentration surfaces surrounding the carbides. So this is the sensitized sample. So this is an 8 atomic percent chromium isoconcentration surface. So in these regions, the chromium content is close to 8%. Now, if you want to see where are increasing amounts of chromium, so this is how it changes. So 10% is distributed like that, and 12% is distributed there, 14% is distributed there, and 15% is distributed there. So that gives us a three-dimensional visualization of how the chromium is distributed surrounding the carbide. And it's very interesting to see planar features of these isoconcentration surfaces. It represents a classical diffusion profile that comes from a diffusion-induced uh, nucleation and growth of the carbide precipitates. So you have, as you come closer to the carbide, the chromium content is decreasing in a very uniform fashion. But now, if you look at the UNSM treated material, first of all, there is no region in the sample that is having a chromium content as low as 8%. In fact, even 10% is very sparse. So the lowest chromium content that is statistically relevant in the sample is 12% chromium, and that meets the threshold requirement for passivity. And that's telling us why these materials are much more corrosion resistant than the sensitized material. And then if you look at where higher chromium contents are situated in the sample, you can see they're much closer to the precipitate as compared to the sensitized material. This is where 15% is, and this is where 16% is. They all come within the field of view here. And the other interesting aspect that we noticed is the faceted nature of these chromium isoconcentration surfaces. So in the sensitized material, they're all planar in nature, but if you look at the treated material, they are faceted like that. So that was very interesting for us. So that's telling us that the deformation mechanisms are somehow interacting with the chromium distribution profile to form these kind of faceted features. So which is where the answers to our questions lie. So we because the faceting is there, and we know that from TEM evidence that there is deformation twinning, we wanted to see if this faceting is in any way connected to the twinning that's occurring. So fortunately, in this data set, we had some kind of crystallographic information, so which you can see from ion density maps in atom probe data. So we took a representative ion density map from this horizontal cross section in this atom in the data set, and we saw two poles separated by an angular spacing of 20 degrees for the in the reconstruction. So fortunately, we had prior EBSD data from the region of the atom probe liftout, and we knew that the analysis direction of the atom probe sample is nominally 111. So that helped us basically to completely characterize the crystallographic orientation of the specimen using the atom probe data and the EBST information. So we had to find another low Miller index crystallographic pole that's at an angular separation of 20 degrees to 111, and the 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 crystallographic directions that meet all these requirements give an orientation shown here. So this is where the 111 lies, and here is 112, bar 1, bar 12. So what is very interesting is the one of the facet of the chromium isoconcentration surface is actually parallel to the 111 plane, which is the twin plane for an FCC lattice. So based on all of this, and considering the fact that deformation twinning is the major mechanism that's accommodating deformation in this material, we came up with a mechanism stating that the process of twin thickening offers a means for homogenization of chromium content within the matrix. So this is a classical mechanism of twin thickening shown here. So by the glide of the Shockley partial, you'll have twin front progression. So we hypothesize that at this region, which is a high energy site, atomic exchange can take place, And as this Shockley partial glides, so if you have a chrome enriched region, you can have homogenization of the chromium content, because there is a driving force for chromium content homogenization, but the twin thickening provides a mechanism for dissipating that driving force. So if the Shockley partial glides through this region, you can kind of eliminate the chromium concentration gradient. That's just a schematic representation for the purpose of understanding. So the summary of our observations is that the atom probe measurements reveal a nanoscale chromium content homogenization within the austenite matrix. It's not that the chromium is coming from the precipitate into the matrix, but the homogenization is taking place within the matrix. And the lowest chromium content is above the threshold chromium content required for passivity, which is what is primarily restoring their corrosion resistance. And the redistribution is most likely being facilitated by deformation twinning. So that's the kind of that was the take home message for us from all of this work. So we had both electron microscopy and atom probe tomography, working together to, help us answer crucial questions fundamental questions related to the process and the phenomena. So I'll end with a set of conclusions here. Basically, the UNSM treatment is a surface peening technology that can induce deformation-induced effects up to a range of hundreds of microns in the material. High strain rate deformation gives rise to deformation twins and subsequent martensite transformation. And this interacts with the chromium distribution in the microstructure to kind of homogenize the chrome depletion and bring the chromium content about the threshold required for passivity. So, and that's what is leading to effectively heal the sensitized microstructure. So you're all welcome to read the full paper. It has all the details in Metrans, and Kamika has just prepared an application note on this topic, and this will be up very soon on the website. And with that, I thank you all for your attention, and I'd be happy to answer any questions.
Oh, thank you so much, Dr. Sassadar. And if you don't love metallurgy after that talk, I think that, that's a really good indication about how things can really occur at multiple size scales in, macro scale changes being healed by kind of microstructural treatment, and then having the atomic level understanding of that process. So, that to me is fantastic.
Yep.
Okay, we can move to the live Q&A now. And so if you have any questions, feel free to upload those through the live Q&A box, and we'll get started with answering some of them. So the first one is less of a question than a comment. Hello, Dr. Kasturi. Thank you very much for the talk. So, I agree. And then we just have some
Pleasure.
coming in now. I have a few questions as followed. How do you select the PSI angle when performing the residual stress measurement using a sine square method?
Yeah, so I mean,
that's psi angle, not PSI. Sorry.
Yeah. So it's the classical sine square psi method. So basically, when you have standard methodologies that are documented in the literature, you measure a given peak, let's say any peak that gives good intensity, like a 111 or any peak of your choice, and then you measure that at a range of psi angles. It's not one psi angle, but it's a range of psi angles, and you can go as high as it allows. Basically, as you go to increasing psi angles, the measured X-ray counts decrease, but typically you can go from 0 until about 70 degrees or so, and then you make a plot of the interplanar spacing that you're measuring as a function of the psi angle, and you make a plot, D versus sine squared psi, and there's a method to calculate the residual stress from that. So yeah,
Okay.
that's a standard calculation.
And then this is a two-part question. So the second part
Okay. Yep.
is there any further characterization to confirm the alpha prime martensite as their lattice parameter is very close to that of the alpha phase? So alpha and alpha prime.
Yeah. So we are nominally calling it martensite because it's a deformation-induced transformation here. I mean, at least we were happy with the characterization that we did, and we didn't see the need for really saying if it's different from alpha and or alpha prime. So yeah, that's where I would leave it at.
And then as they keep coming in, I have a question. Were you able to see any changes of chromium content in the matrix after the UNSM process? You know, if you looked at the matrix without the carbides, as you can in atom probe data, you know, are you
Right.
able to see any frequency distribution changes, things like that?
No. So I mean, yeah, we did measurements even away from the carbides, and the chromium content is very homogeneous. So there's no clustering or anything like that that's occurring. So we tested for its, I mean, statistically, we don't see any clustering. I wouldn't expect that also in this material from a thermodynamic point of view. It is stable. So
Great. Okay, great. And then, you know, do you think that this process could be applied to different geometries, you know, kind of a circular pipe, something like that? Because as I understand, you know, those weld seams are really a big failure point.
yeah. Yeah, so not a lab scale setup, but you can definitely engineer a setup at the industry scale to actually work with curved geometries. And there is work being done at institutes in the US that we are aware of who have done work on curved surfaces. So these peening technologies have been applied to curved surfaces. So that's very well possible.
Yeah, great. And then, you know, as they keep rolling in, I had a question about the weld points. You know, are you sampling any different chemistry in those heat affected zones from the weld? You know, how big are those anyways? I don't have a
Yeah,
good sense of that.
yeah. So I mean, that's going to be extremely dependent on the geometry of the particular weld. So in this particular, let's say the canister weld, it's very big. So the Professor Sridharan can correct me if I'm wrong, but the the thickness of the plate is close to a half inch, and it's a big fusion weld. So so technically, the heat affected zone is strictly heat affected. It's not, uh, uh, you know, affected by the diffusion
Right.
from the solid state weld. So um, in the fusion weld region and very close to that, you will have chemistry differences. And that's a very different region of the material that will have very different grain structure and mechanical properties, and the composition will depend on the filler material that you use, but the heat affected zone typically is not affected compositionally
Okay.
by the welding process.
Okay.
Bulk composition is not affected. The microstructure locally it's varying here, but the overall composition is the same because there is no liquid phase mixing, and that could extend several millimeters, I think.
Oh,
Quite big, yeah.
excellent. Okay, so we have another question from an attendee. Very interesting findings. I just have one doubt. Can we use ion density maps at a plane instead of showing individual chrome ICS, so isoconcentration surfaces, 8, 10, 12, 14 atomic percent, to show the chromium distribution from the carbide interface?
Yep, absolutely. I think, yeah, that's a good way. I mean, atom probe data is extremely versatile and you can have a number of different visualization methods. I think, yes, you're right. You use an ROI of your convenience, and then you plot a chromium ion density variation, you can see this difference. Yes, absolutely.
And I think, you know, the proxygram is also a useful tool here
Yep.
because, you know, each calculation we do in Atom Probe, they really hit at different spots of that analysis space?
Yep.
That's a great question. Let's see. A question about the cementite and chromium carbides. Do you see any bimodal distributions when you sample these? Do you have enough data for that to
Yeah.
see distinct cementite and chromium carbide?
Yeah, that's a great question. We don't have cementite in this material, so we're looking at different. So cement, because chromium has so much affinity for carbon that when there is chromium, it doesn't allow cementite to form. And I would say we don't have enough data to say what's the distribution of, let's say, like in this figure, you know, this sized carbide to this sized carbide. So I don't know if you can see my pointer now, but
Yep.
yeah. So, but yeah, I mean, that is something that we'll have to acquire more data to validate.
Okay, we have another question coming in. Regarding the APT results, there was one slide you showed the evolution of microstructure with chromium content. As I know APT is a destructive analysis, how could that result be captured with the sample, or am I wrong?
So I guess the question is referring to this.
Right.
So yeah, so that's a very nice thing about Atom Probe data, that once you acquire a data set, you can basically look at it from, I mean, using different segmentation tools, you may want to call it. So here it's the same data set. I'm not looking at different data sets, but this is the same data set, but now I'm highlighting, different aspects of the microstructure. So in this image, I'm highlighting only those regions which have 8% chromium. Here, I'm highlighting those regions with 10% chromium. Here, those regions with 14% chromium. So yes, it's destructive. You kind of consume the sample, but then now you have that data, and then you can look at that data, in any number of different ways that you want to look at it. So like somebody has suggested, they may want to look at the ion density variation. So you can use the same data set and look at the ion density variation. So all of that is possible. I hope I answered the question.
Yeah, I think that was good. And I think that's it for the customers. I just had one more question here, Sasadar. Do you see that kind of cubical geometry in other techniques, SEM, TEM?
Yeah, so that's another, great question. Something that we couldn't, the three-dimensional morphology is something we could not see in any other
TEM
technique.
maybe,
Yeah,
or
we had TEM images of carbides. Few at least, if not many, and we could not see the morphology. So the other thing is that, so you can see the morphology difference between, the sensitized carbide and the treated carbide so distinctly here. That was something that I didn't emphasize sufficiently. So thanks for the question. So like all the facets that you see here, maybe this is a better slide. So all the faceting that you see here, and the way the carbide shape has changed compared to the sensitized carbide. So that is all something we can see only by atom probe tomography.
Right.
So
okay, well, if there's no other questions, I don't think there's any more online. I really appreciate Professor Sridharan for joining us with your experience from the University of Wisconsin. It's just wonderful to have you here. And of course, our Dr. Kasturi, one of Kamika's own. So thank you for presenting your work. So next month, we will do a geologically focused webinar. I hope you can join us again. And thanks so much for joining us today.
thank you. It was a great pleasure.
Okay.
Thank
Bye,
you.
everyone.
Bye.
Thank you.